So we're starting a new unit, and in this unit, we're going to be looking at confidence intervals, particularly in the first couple of lectures, particularly for the mean. So let's just review the purpose of statistics, okay? Purpose of statistics is to take something from a sample, a statistic from a sample, and to estimate some sort of parameter, which comes from a population. Okay, now we just did this, and we're going to talk about this in a lot more detail in the third lecture for this unit. But just as an idea, okay, they just did this study on the coronavirus in New York City, and they wanted to try and figure out how many people have actually been infected. So some of you may be familiar with this study. So what they did is they tested 3,000 people randomly for the antibodies, and they found that 13.9%, or 417 people tested positive out of that 3,000. So they're using that to say, okay, well, in New York, that means that approximately 13.9% of people have had the coronavirus and recovered, okay? Okay, that's what we try to do with statistics. So statistics, the purpose so remember, statistics are taken from a sample. So the purpose of statistics is to estimate parameters, and parameters are taken from a population. In other words, we're taking what we know about a population, about a sample, and we would call it extrapolating, okay, because we're taking what we know and then kind of extending it. So we're extrapolating. I'll say extending. Okay, so what does this mean? Okay, this means that if we take the mean of a sample, we're saying that's approximately the mean of a population. The thing is that that's very rare, actually, that the mean of the sample is exactly the mean of the population, right? It wouldn't make sense that if we take 3,000 people and we say, what's the average number of hours that you sleep per night, that's going to be exactly the same as the average number of hours that everybody in the population sleeps per night. It wouldn't make sense that it's exactly the same. So what we're going to do here is we're going, and this is what the whole unit is about, is we're going to establish some sort of interval. Okay, and we're going to say, okay, well, if this is the mean of the sample, then we could take this mean and we could say, well, the mean of the population falls somewhere within this interval. Okay, what the interval is going to be is going to depend on how confident we want to be that it's correct. Okay, so we would say, okay, well, we're 95% confident that it falls within this interval. We're 99% confident that it falls in this interval. Or we're only 50% confident that it falls within this interval. So if the mean number of hours that a U.S. adult sleeps, if we take 3,000 people, is 6.2 hours, we could say, okay, well, in the population, it's probably not exactly 6.2. Maybe it's between 5.5 and 6.5, okay? Or 5.5 and 6.8 if we're being accurate, okay? So what we're trying to do, and the reason why I said if we're being accurate is because the sample mean is going to be the exact center of this interval, okay? So let's make the number simple. If we say in the sample, the average number of hours that somebody sleeps per night is 6, then we might say in the population, it's between 5.5 and 6.5. And we're going to say how confident we are about that, okay? And the smaller the interval, okay, really I should say, as when we increase the sample size, okay, then we're also increasing the accuracy of our estimate. So in other words, a sample of 3,000 people will be more accurate than a sample of 50 people, but it'll be less accurate than a sample of 30,000 people, okay? So how do we do this? Well, let's start with something called a point estimate. So point estimate is simple, okay? The point estimate is where we start. It's the exact middle of that interval. So the point estimate for the population mean is going to be the sample mean, okay? So just very simply put, we're using the sample as a point estimate for the population, okay? So let's just write that down. This is just more about terminology than about the complexity of what we're doing, okay? So point estimate is, we call it a single value estimate because it's not a range, okay? It's just one number. Okay, so for example, we can use the sample mean as a point estimate for the population mean. Okay, so again, if the mean number of hours that somebody sleeps at night is 6 in the sample, then we're going to start off by saying the mean number of hours that somebody sleeps in the population is 6 as well. But this is just an estimate, and we're going to create an interval instead, okay? Okay. So let's also include this thing that if we increase the sample size, we increase the accuracy of our point estimate. Because that's important. And there actually are ideal sample sizes, okay? So, and that's going to be based on how big we want that interval to be. If we want it to be a very small interval, then we could figure out, okay, well, then we need this many people in our sample. And if we want it to be a really big interval, then we would say, okay, we need this many people in our sample. So we'll be doing that as well today. Okay, So let's just take a simple example, okay? If we take the average number of hours that 40 people taking Math 150 study for the class, okay, our mean would be a point estimate for the average number of hours that every student studies for Math 150, okay? The sample mean is the point estimate for the population mean. It's not equal to the population mean, though, okay? In fact, it is very rare that our population mean is equal to the sample mean, even if the sample is huge, okay? So what we're going to do, and I'm going to put this in a different color because it's kind of like the key to this whole lecture. It's also the key to the whole unit, okay? So we're going to use X bar, remember that's the sample mean, okay, to find an interval I said it in which, but it's really which. An interval which we think the population mean falls into. Okay, so we're using the sample mean in order to estimate an interval for the population mean. Okay, now this range of this interval is called the margin of error. Okay, so for example, okay, so let's say I'm going to go back to black. So suppose X bar is 12. And we find an interval, and we're going to discuss how to do this. That is from 11.5 to 12.5. Okay. So notice that X bar is exactly in the center of the interval, right? What this means is that the margin of error of our estimate is 0.5. The margin of error Why is it 0.5? Because 11.5 is 12 minus 0.5. And 12.5 is 12 plus 0.5, right? This is where the 11.5 less than 12 less than 12.5 comes from. Okay, so the margin of error is 12.5. Okay, how do we determine the margin of error? It's based on our level of confidence, okay? How confident do we want it to be that it falls within this interval? That is our level of confidence, okay? So let's define that. Okay, so There are two ways that I'll describe it. The first way would be how confident we are. Our parameter falls within the interval. A more mathematical way of talking about it is the probability that our mean falls within that interval, okay? It's the same thing. And I say the mean, but it actually should be the parameter, okay? Because today we're talking about mean, but we might not always be talking about mean. So in other words, we're saying the probability that there is a, for example, because you're going to see this number a lot, there's a 95% probability or a 95% chance that that our mean actually falls within the interval 11.5 to 12.5. Okay. Or maybe there's only a 90% chance, or maybe there's a 50% chance that it falls within this interval. Okay. Okay, so now that we know all of the things that we need to know, that we need in order to determine this interval, let's figure out how to find it, okay? So what we want to do is we need to determine our level of confidence, okay? Then how confident do we want to be that it falls within a certain interval? Then we have to actually figure out what interval it should be based upon that level of confidence. Okay, the interval we determine using the margin of error, okay? And then that's it, okay? So we have to do a few things. We have to first determine the level of confidence, or decide on the level of confidence. Then we're going to come up with a point estimate, which is easy because that's just essentially given to you, okay? And then we're going to come up with a margin of error based on that level of confidence. Okay, so let's just write that down, the order in which we're doing things. And whether you do the point estimate or the level of confidence first, it doesn't make a difference. And these are things that are essentially, the point estimate is given to you because it's based on the sample. The level of confidence is something that you decide, okay? Something that you're making a decision about. And sometimes the problem is telling you, the problem makes the decision for you, okay? Or you make the decision. Okay, and what you're really finding is the margin of error. So your process for finding an interval is to find the point estimate. So in this lecture, it's just going to be the sample mean. Then you're going to decide on a confidence interval. I want to be 95% confident it falls within this interval. And then finally, you're going to calculate your margin of error. Okay, how do we identify this level of confidence, and how do we figure out the margin of error? We do it using the normal curve, okay? So we have to use the normal curve. So we're going to be asking ourselves the same questions. Either the data has to be normally distributed or n has to be greater than or equal to 30. Okay, so this is the same thing that we did in the previous unit where we're talking about an approximation of a normal distribution. Okay, so to do this, this is the same thing that we did. Either the data is normally distributed or n is greater than or equal to 30. And this is the central limit theorem. Okay, remember n is the sample size. This is the central limit theorem, that when n is greater than or equal to 30, it approximates a normal distribution, okay? Again, the bigger the sample, the better, because the more closely it fits with a normal distribution, or it's already normally distributed, so it doesn't matter, okay? Okay, so let's find the margin of error. So first of all, in order to find the margin of error, this is kind of a simple process that you've already done already. Okay, so margin of error is E. I'm going to put that in here. That's what we use to represent E, to represent the margin of error. Okay, so to find the margin of error, first of all, we need to know the level of confidence. And that level of confidence, we use C. Okay, and again, level of confidence is we believe there is a 95% chance it falls within this interval. There is a 50% chance it falls within this interval. There is a 99% chance that it falls within this interval. Okay, so the margin of error is equal to Z, the Z-score for that confidence level, okay, and we'll talk about that in a second, times the standard deviation of the sample, okay? So this is like a sampling distribution, okay? Just like a sampling distribution. Remember that the standard deviation of the sampling distribution is sigma, which is the population standard deviation, over the square root of n. Okay, so notice this assumes that we know the population standard deviation. In our next lecture, we're going to say, okay, well, what if we don't? Because that's not always realistic. But in this case, okay, we're assuming that we know this. So if you don't know this, and again, it'll be given to you if you're doing a problem, okay? If we don't know this, then we can't use this method. Okay, and just to give you a preview, it's really not that much different if we don't know sigma, okay? So don't panic. This is the population standard deviation. I keep writing these things, but to be honest, at this point, you should know this, okay? This is, if you don't know that sigma is the population standard deviation, you should be going back and re-looking at a lot of these videos. You should be going back to your notes at the beginning of the semester, because that's something that you should be really familiar with. Same way that you should know that sigma of x bar is sigma over the square root of n. We've done this so much in the last unit that should be automatic to you. Okay, so what is this ZC? Okay, we've actually done this before, so don't worry, this isn't anything new. There's no real new information here. Okay, ZC is based on the normal curve, which is how you know that you need the population to be normally distributed or n is greater than or equal to 30. Okay, so I'm gonna put this in here also. I put it up immediately above. The sample has to be a random sample. So if we go back to the number of hours that people study in Math 150, if we took this class, it's not really random. You all have the same professor, you're all getting the same material, you're all getting the same quizzes. It's not really random. Random would be literally pulling people out, just everybody who's in Math 150, put them in a room and just pull out people at random. Okay, so not in any particular class or section, not meeting at any particular time, not learning in any particular way, not getting any particular type of test questions, just completely pulling at random. Okay, so that's why I wanted to put this in here. The sample must be random. And also we need to have a normal distribution because of this ZC. Okay, the Z sub C. So I say Z sub C because the C is down here as a subscript. This Z sub C is based on the normal curve, okay? So if we don't have a normal curve, then we can't use this. So I'm rewriting this, even though it's written immediately above. So this is always something that you need to check for. And if neither one of these is true, then you have to stop. You can't do this. Okay, why are we so dependent on the normal distribution? Because it's symmetrical, okay? So here's what the Z sub C is. And again, we've done this. So it's based on the normal curve. Okay, remember that this is your mu is over here. And what you're doing is you're saying that falls within a certain interval. It's a probability. And if you remember, okay, probability is the area under the curve. So if we say that we have a 95% confidence interval, we're saying that this range is 95%. We're 95% confident that it falls in this interval here. So this is a percent sign. I don't know why it's not coming out. I'm going to try it again. Okay, that's better. We're 95% confident that it falls within this interval, okay? So this is negative Z sub C to Z sub C. So how do we find the Z sub C? Okay, notice we want a positive value, okay? So that's because our margin of error, we want it to be positive. This is our range. Our range is from negative z sub c to z sub c. So how do we find this negative z sub c or z sub c? What we do is we do exactly what we've done before. We have to go to the z-score table, okay? What are we looking for in the z-score table? Well, if this is 95%, then we need to subtract the 95% from 100%, okay? Or 1 minus 0.95. Okay, C is our decimal, okay? So if we have a 95% level of confidence, C is equal to 0.95. So to find Z sub C, we first do 1 minus C. Then we take that and divide by 2, right? Because this means that we have 5% on the outside. So what's this? This is 2.5%. Okay, that's 2.5%. Or 0.25. Then we find that in the z-score table. Okay. Once we find that in the z-score table, we have z sub c. The sigma x bar is given to us because we know the sigma and we have to know the sample size, okay? And we calculate the margin of error. And then our range for our mu, we subtract the error and we add the error. Okay, so let's do an example. So first of all, the margin, I should put this. I'm going to put this up here. I just want to give you one more definition. Okay. I'm going to put it in pink. The definition I want to give you is x bar minus mu is called a sampling error. Okay, now most of the time you're never going to know this, okay? This is the actual difference between the sampling, between the sample and the population mean, okay? I just want to give that to you as a definition. Most of the time, you will never know this because you're not getting the actual population mean. The whole point of using a statistic is that we can't find it for a population. So this is just a side note, okay? I just wanted to give you that definition. Okay, so let's take an example where we actually find the margin of error, okay? And again, this seems very complicated, but you're finding a point estimate that's given to you. You're deciding on a confidence level, which is most of the time given to you. And then you're calculating the margin of error. How do you calculate the margin of error? Well, the only thing that you really need to find is Z sub C. You know how to find Z sub C. You take the confidence level, you subtract it from 1, okay? Because what we're doing is we're saying we're 95% confident it falls within this interval. So outside of the interval is 5%. Okay, if it's a 95% confidence level, then we're going to divide by 2 because that gives us how much is to the left, okay? And that's what we want when we're using a z-score table. So we go to the z-score table. This is all stuff that we've done. We go to the z-score table, we find the z-score, make sure that you use the positive number, okay? And then you're just adding and subtracting your margin of error after plugging into the formula, okay? So let's do this. Let's find an actual margin of error, okay? So we ask 40 college athletes how many hours they spend on required athletic activities. We want to have a 95% confidence level or level of confidence for the mean number of hours. Given a population standard deviation of 2.3 hours. Okay, so we're going to develop an interval here. Okay, so what's the first thing that we need to do? First thing that we need to do is check that the data is normally distributed or n is greater than or equal to 30. Always, always, always check this. Now, I gotta tell you, common sense is gonna tell you one of these things is always going to be true because we're giving you the problem and we're asking you to make a calculation. But if you're doing this on your own, okay, then you want to check these things, okay? And there will be times. So for example, if we have that coronavirus study, if we go back to that, some of you may say, okay, well, 13.9%, that's the number for the sample. But is that a really accurate representation for the population? What is the interval for the population? So this is not the same thing because we're not asking people for a number of hours, right? We're figuring out, do they have it or do they not? So that's more binomial. So that's why we're not doing it in this particular lecture. But if you get that, you want to know, well, how accurate is that a representation of the population? How confident should I be that it falls within an interval? I want to create an interval where I'm 95% confident it falls within that interval, or I'm 99% confident it falls within that interval. So that would be an example where you're getting certain information and then you're saying, okay, but how accurate is that information? Okay, is it really that? Okay, if for the sample it's about 14%, does that mean that I'm 95% confident that it falls between 12.7% and between 13.7% and 14.2%? Or does that mean that I'm 95% confident that it falls between 10% and 16%, which is very, very different, right? These are different numbers. If you're saying you're 95% confident that, yeah, it's essentially 14%, or you're 95% confident that it's somewhere between 10 and 16%, those are very different things. So that's something that on occasion you'll hear a statistic and you want to calculate it on your own, okay? So in these, yes, when you're given a problem, most of the time, I would say all of the time, the data is either normally distributed or n is greater than or equal to 30, but you still need to check, okay? And it is, okay? It doesn't say that it's normally distributed, but if we look at our sample, so it will say, okay? If the data is normally distributed, it'll say, you're not guessing. It will say the data is normally distributed. Okay, so since it doesn't say anything, since we don't see the word normal distribution or normally distributed, then we have to look at the sample size. And the answer is yes, sample size is 40. Okay. Okay, so the next thing that we have to do is we have to find C. And again, this is either given to you or they're telling you to decide. They're saying, come up with an interval and come up with a confidence level. Okay, so you're deciding. In this case, it tells you, it says you have a 95% level of confidence. So what is your C equal to? C is equal to 0.95. Okay. Third thing that you're doing is you're finding Z sub C. Okay, so we're going to do 1 minus C. That should be a 1 minus 0.95. Which gives you 0.05. And then you're going to do 0.05 divided by 2, which is 0.025. Okay. So in the z-score chart, so here we're going to go to our z-score chart. Okay, it's going to be in the negatives. Okay, it's going to be in the negatives. We're looking for 0.025. So if we go to 0.025, it's right here. Okay, 0.025. So we're finding the z-score. So we're looking inside the chart, not at the sides. We're looking inside the chart for 0.025. It's right here. So the row is 1.9 and the column is 0.06, so it's 1.96. Now notice this is negative, but we take the positive, okay? So our z is equal to 1.96. Okay, now we're going to find our margin of error. I meant to put that all in pink. Oh well. I meant to put our instructions in black and our work in pink, but I'm not going to rewrite all of that. So E, our margin of error, is our Z sub C times sigma x bar. Okay, Z sub C is 1.96. And sigma x bar is our sigma over the square root of the sample size. And the sample size is 40. Okay, so this is equal to Z sub C sigma over the square root of n. Okay, and what do we get here when we do this? We get 0.7. So now we determine our interval. I have to give you the mean number of hours for the sample. So I'm just going to add that in here at the top. And x bar is equal to 21.1. Okay, sorry about that. So we're going to do 21.1 minus 0.7, and we're going to do 21.1 plus 0.7. Okay, so this is x bar minus E and x bar plus E. We're doing our point estimate plus the margin of error and the point estimate minus the margin of error. So we get 20.4 here and we get 21.8 here. So what does this tell us? This tells us that the population mean is somewhere between 20.4 and 21.8. Okay, so this is the range for the population mean. And again, this is with a 95% chance, a 95% confidence level, okay? Okay, let's change this, okay? Let's do it where instead of, let's do another example. Okay, we're going to do exactly the same thing. So let's say the mean number of minutes. I think we did something similar to this. The mean number of minutes. A customer spends in one trip to a department store. Is 62. Taken from a sample of 70 people, of 50 people. Standard deviation is equal to 15.1 minutes. Okay, so let's find a range for, or really a margin of error, right, with a 95% confidence level, okay? And I'm using confidence level and level of confidence interchangeably. Okay, we're going to repeat this, but we're going to repeat it for a 90% confidence level. That's why I have an A and a B. Okay, I don't have the B yet, but it will. Okay, so let's figure this out. So again, we're going to go through the whole process again. We're going to determine first, is it normally distributed? Or is n greater than or equal to 30? And in this case, it doesn't say normally distributed, so we have to look at the sample size. And n is equal to 50. So yeah, it's normally distributed, which means we could go on, okay? In this case, C is equal to 0.95. Okay, so we need to find Z of C, and we already know that we're going to find, we know from the previous problem, okay, that we're going to find a Z-score that corresponds to 0.025. But again, let's just, we're doing 1 minus 0.95, which is equal to 0.05. And then we're going to do 0.05 over 2. So this is the same process, and it turns out that it's still a 95% confidence level, okay? So Z sub C is still 1.96. Okay, so this is the first step. This is the second step. This is the third step, okay? And then finally, we want to find our margin of error. So we're going to take 1.96 and we're going to multiply by the standard deviation over the square root of the sample size. Okay, so that comes from here. Okay, the Z-score times the standard deviation over the square root of the sample size. There's just something I want to make sure. I want to change this. I wrote mu minus E and mu plus E, but it's really not mu, right? It's really X bar. Because if we know mu, then we don't need to do this. Sorry, I just wanted to put that in there. Okay, so what is 1.96 times 15.1 over the square root of 50? It's 4.19. Okay, so let's find the actual range. So X bar minus E, well, our X bar was 62, so 62 minus 4.19 is equal to 57.81. And an X bar plus the range, plus the margin of error, is 66.19. So our population mean falls between 57.81 and 66.19. So again, there's a 95% chance that it falls within this range. Okay, so now we're going to do exactly the same thing, but we're going to change the confidence level so that you get a little bit of practice with that. Even though you've done it in the previous unit, I just want you to see it again here, and I want you to think ahead of time. Okay, the food for thought. If we decrease the confidence level, do you think that the range is going to increase or decrease? In other words, are these numbers going to get closer together if we're decreasing the confidence level? Do you think that it would be, let's say that we said it falls between 60 and 64. Would we be more confident that it falls between 60 and 64, or less confident that it falls within a range like that? Okay, so I want you to think, in other words, I want you to think about if the interval is smaller, are we more or less confident that it falls within that interval? Okay, so let's first do it, and then we'll talk about it. So we're going to find the interval for mu. With a 90% level of confidence. Okay. So again, is the data normally distributed, or is n greater than or equal to 30? We already know this. Okay. So our first step is to check for the normal distribution. Okay, again, if n is greater than or equal to 30, then we're saying it approximates a normal distribution. I don't know why it got this weird tail here. This is just greater than or equal to. Okay, that's the first thing. Our second thing is to determine our level of confidence. So our level of confidence here is 0.90 now. Okay, now we have to find our z-score. So it's 90% in the middle. This is now 90%. So if it's 90% in the middle, it's 10% on the outside. And how much is it just over here? It's 0.05, right? Over there, it's only 0.05 or 5%. I'll rewrite it as 5%. Okay, it's a 5% chance. So it's 5% on the left, 5% on the right. That gives you 10%. Okay, 90 plus the 90% in the middle, that's your 100%. 10%, you have to divide it in half, right? 10% is on the outside. You're dividing it in half so that you get just the piece that's on the left. So we're doing 0.1 over 2, which is equal to 0.05. So now we have to go to the z-score chart. Okay, z-score chart you cannot come up with this on your own. Okay, so you will get the z-score chart. So we go and we look for 0.05. 0.05 actually falls exactly between 1.64 and 1.65. Okay, so since it falls exactly between, we can't choose the closer one. So we take the number exactly in the middle. So it's exactly between . So we would say it's 1.645. If it's not exactly between, choose the closer number. So just like before. Okay, so now we plug in. RE is equal to 1.645 times 15.1 over the square root of 50. So nothing else changed. It's just that z-score that changes. And for this, we get 3.51. So now let's find the interval. So we're adding the 3.51. So we have 62 plus 3.51, which gives us 65.51. And then we're going to subtract it. So this is 58.49. Okay, so this tells us, okay, that the interval is between 58.49 less than mu less than 65.51. So let's go back and look at what we found before. This interval starts at 58.49. This interval starts at 57.81, which is earlier. This interval ended at 65.51. This one ended at 66.19. So there's only a 90% chance that it falls within a smaller interval. This interval is smaller, okay? That kind of makes sense, right? The bigger the interval, the more sure that we're going to be that it falls within that interval. If I said, okay, well, how confident are we that it falls between, that the population mean falls between 40 and 80? We're going to be really confident that it falls somewhere between 40 and 80 if the sample mean is at 62, okay? If the sample mean is at 62, we can say, yeah, I would say I'm, really, really sure. I'm almost 100% sure that it falls between 20 and 100, okay? Right? The bigger the interval, the more sure that we are that it falls within that interval. So as our level of confidence increases, our interval is going to increase. Here our level of confidence decreased. So our level of confidence is going to decrease as that interval gets smaller and smaller. And you could see it here, okay? Think about it in terms of the picture. How do we make this percentile increase? We increase the size of the interval, right? We increase the area. So as the level of confidence increases, so does the margin of error. Which, kind of by definition, because we find the interval using the margin of error, which means the interval increases as well. Okay, visually, this makes sense. Right? If this is 90%, how do we make the 90% bigger? We have to increase this. This would be 95%. Okay, so I don't know why that is. Okay, so it makes perfect sense. I'm going to rewrite this. I apologize. I don't know why it came out so ugly. So it makes sense that something about the notes that it's not coming up. Okay, that's better. Sorry, it's off center. It makes sense that as the level of confidence increases, the interval is going to increase. Okay, so this is visually, but you could also think about it, just make the interval really, really large. Okay, if the sample mean is 62, then we're going to be very, very confident that our population mean is between 20 and 100. We're going to be a little less confident that it's between 50 and 80, okay? And we're going to be even less confident that it's between 58.5 and 65.5. So as we decrease this interval, our level of confidence is going to decrease as well, okay? If it's at 62, I'm not going to be confident at all, okay? I'm not going to be very confident that it's between, let's say, 61.5 and 62.5, okay? So if we said, oh, well, it only has 50% level of confidence, then this number is going to be very small, okay? Okay, so let's go backwards, okay? So what is a good sample size? So here we're going backwards. We want to know how many people we should ask in order to be 95% confident that it falls within a certain range. Okay, so it's kind of the opposite. We want to improve our estimate without increasing the interval. Okay, but we are going to increase our sample size. Okay, so we're saying, how can we improve our estimate without increasing our margin of error? Okay, so if our margin of error is 1 hour, not 1 hour, 1 minute, how can we improve that estimate? How can we become more confident in that estimate? How do we do that? We increase the sample size. Okay, so we can become more confident in our estimate as we increase the sample size. Okay, the larger the sample size, the more accurate the estimation. but we don't want to ask more people than we have to. Okay, we don't want to say, okay, I want to be 95% confident that it falls between 61 and 63 minutes, okay, that the mean, taking the problem that we just did. So taking this problem where we were talking about 62 minutes spent in a department store, I want to be 95% confident that it falls between 61 and 63 instead of between these numbers, okay? But I don't want to ask 4,000 people if I don't have to. I only asked 50 people. Why would I ask more people than I need to? So we want the ideal sample size. We want the smallest sample that would allow us to have that confidence level, okay? So how do we do this? It's really simple. We just take the margin of error formula and solve for n. Because now n is going to be our unknown. Okay, so our margin of error is z sub c sigma x bar. We know that sigma x bar is sigma over the square root of n. Okay, so we're going to solve this for n. So we can leave out this middle thing. Okay, because what you're being given is sigma. You're not being given a sigma x bar. Okay, if you were given sigma x bar, then sure, you can use that. But we're assuming that you're not. Okay, that what you're given is sigma. So we're just going to take out that middleman there. Okay, so here's how we're going to do it. Let's start. So I'm going to go through the algebra with you, but in the end, the algebra isn't all that important, right? But I want you to see where it comes from. So what we're going to do is we're going to multiply both sides by the square root of n to get rid of it on this side so that we don't have a denominator. Okay, so the square root of n is going to cancel here. And we're going to have the square root of n here. And what we wind up with is e times the square root of n is equal to z sub c times sigma, okay? But now we want n alone, so we're going to divide both sides by e. This is all to help us get n by itself. The e's will cancel. So notice we multiplied both sides by square root of n just so that we got it out of the denominator. Okay, so what does this give us? This tells us that the square root of n is equal to z sub c sigma over e. But we don't want square root, so we're going to square both sides. Okay, so we square both sides, that gets rid of the square root. So now we have what n is equal to. So we have z sub c sigma over e squared. Okay, so this would be our sample size. So just a note, if n is not an integer, because most of the time it is not going to be, then you're going to round up. Okay. Okay, so let's just take a bunch of examples. Okay, and say, let's go back to the college athlete example. Okay, so the college athlete example, so I'm not gonna put normally distributed or anything. I'm just gonna go back to exactly what we did. Sorry, I'm just trying to find it. Okay, so the college athlete example was we had 40 college athletes. Told us the number of required athletic hours. The information that we got was that X bar was equal to 21.1 and sigma was equal to 2.3. Okay, so let's find how many people do we need in the sample? How many college athletes? Let's take out the 40 because that's what we're looking for, sorry. So we're just going to make this college athletes told us. Okay, so what we're asking is how many college athletes do we need to survey to be 95% confidence that our margin of error is 0.5. Okay, in other words, we're saying that we're going from 20.6 is less than mu, which is less than 21.6. Okay, we want to be 95% confident that it falls within that interval. Okay, so here's how we do it. We use our formula. N equals Z sub C sigma over E squared. Okay, we already know and this we already know because we've done the problem, okay? So we know from earlier that Z sub C is equal to 1.96. Okay, just we know that already. So N is equal to 1.96 times 2.3 over the margin of error squared. Now what do we get here? We get, if we put this into our calculator, we get 81.29. Okay, so what does this mean? So 81.29 we round up always. So to be 95% sure, the population mean is in the interval well, I don't want to say is in the interval, has a margin of error. Because remember that our X bar is 21.1 after asking 40 people, okay? So this X bar is irrelevant. So I'm actually going to take it out. Okay, and I'm actually going to take this out too, okay? because again, it's irrelevant. What we're saying here really is, I'm going to fix that too, because I don't want to be inaccurate, right? Is that this is x bar minus 0.5, and that this is whatever the mean is plus 0.5. Okay, so what we're really saying is to be 90% sure that the population mean is within 0.5. That would only be true, so the 20.5 and the 21.5 would only be true if we asked the 82 athletes and the sample mean was 21.1. Okay, so that's why I don't want to put that in, because the sample mean is kind of irrelevant here, right? The sample mean is determined from all of the athletes that we're asking. So what we're saying is to be 95% sure the population mean is within 0.5 of the sample mean, we need to survey 82 athletes. That's what we're saying here. Okay. Okay. Let's do one more problem, and we're going to look at it from both perspectives. Okay. And what this will do is it'll sort of tell you when to do each thing. Okay. So we'll do one more example. We want to find the average number of hours a U.S. adult sleeps at night. Okay. We're going to say the data is normally distributed. Again, remember, because it's saying that it's normally distributed, we don't care about sample size, okay? Otherwise, we would. And the standard deviation is 1.1, okay? So we're going to ask two questions. First question is, suppose we took a sample of 2,000 people. And found that the sample mean was 6.8. Okay. We want to find a 92% confidence interval for the population mean. Okay. Okay, let's do this. We know how to do this. Okay, first, the data is normally distributed. It says so. So it doesn't matter what our sample size is. It just so happens that our sample size is over 30, but we don't even have to look at it. Our C is 0.92. So now we have to find our z-score. So we're going to do 1 minus C, or 1 minus 0.92. I did that again. which gives us 0.08. We're going to take 0.08 and divide by 2. This gives us 0.04. So we go to our z-score chart. So we're finding 0.04, okay? 0.04 is closest to negative 1.75. So remember, you're taking the one that's closest, okay? 0.0392 is further away. This is like 0.0001 away. This is 0.0008 away. So it's closer to 1.75. So we use the positive. This is negative 1.75. We're going to use positive 1.75. Okay, so our margin of error is 1.75 times 1.1 over the square root of 2,000. So if we do 1.75 times 1.1, we get 0.043. Okay, when we do this calculation, we get 0.043. So now our last thing is to do our x bar plus our margin of error and our x bar minus our margin of error. So we're doing 6.8 minus 0.043 and 6.8 plus 0.043. And we get 6.757 and 6.843. So we can make the conclusion that our population mean is between 6.757 and 6.843 with 92% confidence. And that's lower confidence than, let's say, a 95% confidence level. Okay. So our interval is tight, but our standard deviation is small. So it kind of makes sense, right? Standard deviation is only 1.1. The smaller the standard deviation, the smaller the intervals, because we know that the data isn't very spread out. Okay. Okay. Let's ask the question differently. Let's suppose we want a 92% confidence level, a 92% confidence interval. With a margin of error that's equal to 0.1. So we want the same confidence level, but a bigger margin of error. So what does this tell us? If we want to find a sample, if we want to figure out how many people we need to ask, do we need to ask less people or more people? Okay. Well, we said the more people we ask, the more accurate the estimate. Okay. This is saying we don't need the estimate to be as accurate, right? Here, the margin of error is 0.043. Here, the margin of error is 0.1. So if we think about it, we don't need it to be as accurate, so we shouldn't have to ask 2,000 people. So let's find out how many people we need to ask. And we're using that formula from before. We're saying, okay, we're going to use this. Okay, the difference is that the z-score that we're using is the z-score that we found here. It's going to be 1.75 because it's a 92% confidence level. So we already found the z-score. Okay, and I'm going to put z sub c here, just so that you know it's the z-score based on that confidence level. So z sub c is equal to 1.75. We already found that. So n is equal to z sub c times sigma over e squared. So this says we're going to plug in 1.75. We know what sigma is. Sigma is 1.1. And you're given the margin of error. It says you want a margin of error of 0.1. So we're going to figure out what that is. That's 1.75 times 1.1 divided by 0.1, which is 19.25, and we're going to square it. So this says we only need to ask, if we plug it into our calculators, we get 370.6. Okay, what is 370.6 round to? It rounds to 371. So we need to ask 371 people to be 92% sure that it falls within the range of within a range of 0.1 from the sample mean. Okay. Okay, that's what we're being told. Okay, so very quickly. One, we're saying that we can determine an interval for the population mean based on the sample mean. So all of this was about taking the sample mean and saying, okay, it's not perfect. It's not exactly the population mean, but we can create an interval for the population mean. Okay, the interval is going to change depending on how confident we want to be that the mean falls within that interval. The more confident we are, the bigger the interval. Okay. Finally, if we know a margin of error that we want, then we could determine what the best sample size should be for that margin of error and that level of confidence. Okay, so notice we're given two things, a confidence interval and a margin of error. Okay, and the biggest thing is that all of this is assuming we know the population standard deviation. Okay, all of this is assuming we know the population standard deviation. So that I think we put at the beginning. I'm looking for it so that I can box it for you. So I put it at the very, very beginning, right? A known standard deviation, okay? And did I put it anywhere else? Yes, I did. I said on the next page, again, we assume that we know sigma, okay? I'm going to box this again because everything that we did, if we do not know the population standard deviation, this is a completely different process, okay? So that's why I'm boxing it, because it's super important. Okay, and that's why it's in the title here, because if we don't know the standard deviation, the population standard deviation, everything changes. And that's what we'll talk about in the next lecture. Okay, that's it.